Hello, I'm Anna Mackay and today we're looking at geometric scalar multiplication. Now that's not to be confused with the scales of a fish, but it's more closely related to the idea of scales. It's still not quite the same in terms of cooking and measuring, but it's closer to that. And it's different again from scalar products, which we'll look at another time. So a scalar multiplication here, the word scalar, do you know anything about that? So it's referring to a number. So we're doing number multiplication within vectors. So we've got the vector A here. What would 2A look like? So it's two lots of that vector A. Can you visualize what that might look like? So if there's 1A, our second one is attached to the end, and that creates the vector of 2A. So it's double the length, two lots of A there. And that would be written like that. Well, what about negative 2A? So the scalar multiplication here is of a negative 2. So it's vector A in the negative direction twice. Well, yes. So if that would be 2A, then our negative 2A would have the same magnitude, but in the opposite direction. What about a half of A? So think about what A would be, and you want half of that, half the magnitude. So there's A, half A, so that's going in the same direction, but it's half the length. So there's the 4 that we've talked about there. Just to summarise that, if K, so the scalar that would be sitting out the front of A, if that's greater than 0, thinking about which versions of that we had where K was greater than 0, Ka and A have what? What's common about them? They've got the same direction, as you can see that they're going in. Not this one though, because that falls into this category. If K is less than 0, so if that scalar is negative, then Ka and A, those vectors, have the opposite direction. What about if it's equal to 0? What if that scalar is 0? Then the vector Ka would be the 0 vector. It's going nowhere. Now, just a point here, we can never divide vectors. When you get into the topic of matrices, it's the same. You can never divide a matrix, but you can multiply, in this case, by a half. That's the terminology. Although in your mind, you might be thinking that it's the scalar product of a half, not divided by 2. Okay, looking at these examples here, we've been given these vectors, an R and an S, and we have to construct 2R plus S. So what would we have there? Two lots of R, so let's draw that, one lot of R there, and the second one we attach on to the end. So we've got R and R here, and then we have to add on S. So you'll obviously have grid paper. Notice that S is across 2 and down 2. So we'd have this. And then to finish it off, you connect the beginning to the end, and you would write 2R plus S, but put arrows on because we can't do bold. There we are. The grid squares were provided for me. And then the second one here we have is R subtract 3S. So we've got our vector of R to start with here, and now we want to subtract off 3S. So thinking about what S is, normal S would be down 2 to the right 2. So if we want a negative of that, instead of down 2, we have to go up 2, and instead of right 2, we have to go left 2. And we want 3 of those. So from the arrowhead, we're going up 2 and left 2, and then again, using your ruler, of course, and again. And then connecting the beginning of R to the end of those negative 3S, using your ruler please, unlike myself, then we've got R take 3S is our resulting vector. Right. Sketching P and Q if P is equal to 3Q. So it doesn't really matter how you draw these here, just trying to create the concept. Whatever P is, however big, however small, if we had, well no, in this case it's 3 lots of Q, so we should perhaps visualize Q first. Doesn't matter how big and in which direction. If that's Q, P would be 3 lots of that. So if you had 1, 2, 3, that would be RP, which is equal to 3Q. Make sure that they're exactly the same and they're all in parallel in line. The second one there, P is equal to negative a half Q. So imagine what 1Q would look like. Label that, the vector Q. I should be more accurate and put some arrows on these. P is negative 1/2 of that. So we have to have half the length and in the opposite direction. So here we go. There's half the length, that's negative a half Q of vector, and that's our vector of P. Okay, so that's a short one for this time. Next, join me for vectors in the plane, not aeroplanes. Thank you.